Okay. We're looking at distance versus time graphs, which you looked at in Science 10. But it's awkward in Science 10 because you're just learning in Math 10 how to graph lines. And right away in Science 10, we're throwing at you how to interpret lines. And it's a lot to kind of sink in. So we're going to kind of repeat ourselves a little bit here, but try and put it on a bit firmer foundations. Here's what we have. A person walking along a straight line is being timed while their position from the starting point is recorded, and here's the data. We have time, we have distance, and we'd like to graph this. First of all, unless it specifically says different, time always goes on the x-axis. So I'm going to go time, comma, t in seconds, because we have to label our axes on any science graph. On the y-axis, I'm going to put, well, maybe I can fit it in here if I'm clever. Distance d in meters. What else does every single science graph have to have that a math graph doesn't necessarily have to have? Title. I could probably come up with something fancier, but that'll function just fine. Distance versus time. And I need to add a scale of some type as well. So let's see here. What's the smallest time that appears? 1. What's the biggest? 9. Now for time, I do like to include 0, so I'm going to try and go from 0 to 9-ish. How many squares along the bottom? 11? 22 squares. So are you suggesting going up by 2s? I think that's what some people just intuitively did. They said, hey, I got to go 9, I got 11, I got 22. Let's go up by 2s. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. On the test that you folks just wrote, a number of you forgot this step, and I know I haven't gone through the tests yet. I'm still waiting for a couple of more kids to write, and then we will. Distances. What's the biggest distance that appears? 20. 20? I like to get 0, so I'm going to go from 0 to 20. Let's see here. 2, 4, 6, 8, 10, 12, 14 squares. I got to fit 20 in. What would be a good scale? Sorry? Each square, if I got 14 squares and I want to fit 20, what should I let each square be? 2 squares equals 4. Go up by 4s. Let's see, that would be 4, 8, 16, 20, 22. Okay. 2s? Let's see. 2, 4, 8, 16, 2, 4, 8, 10, 12, 14, 16, 18, 20. You know what? Going up by 2s, letting each big square be 4. Each big hash mark. 4, 8, 12, 16, 20, 24, 28. Have we got a scale? Check. We got titles? Check. We label our axes? Check. Now, and only now, can we graph. The first point, can I get it all on here? Barely. Okay, I got it. Well, no, I'll go like this. Looks like 1, 4. 1, 4, that's a point on my graph. And it looks like 2, 6. 3, 8. Yes, I made these numbers up to get a nice pattern. In real life, you'd have some noise in your data. It wouldn't quite be this clean, but that's okay. Is the next one 4, 10? No. Yeah? Looks like I'm going up 2 over 1. Sorry, up 1 over 2. Up 1 over 2. And if I continue the pattern, it looks like my y-intercept is not going to go through 0, 0. And then I'll take out some kind of a straight edge. If you got a ruler, use it. If not, use your calculator or freehand as best you can. I'm going to cheat and use my draw features. Ha-ha. Line. Yeah, there are still rulers up there. If you really could just start bringing your own, for what it's worth. I get that. By the way, in Math 10, you would have asked, can I connect the dots? And yeah, because you're running the entire distance, you're not teleporting from one distance to the next, you're running all the distances in between, we can connect the dots. But in Math 10, you learned that some graphs were disjoint or discontinuous. All right, we've graphed it. Big deal. Huge deal. Huge deal. What's the y-intercept?
2.
If you want to give it as a point, 0, 2, but 2. What's the slope? The most common mistake I saw for slope on the test was this. Look up. Do not write this down. I had a whole bunch of kids go, oh, slope is up 1 over 2. It's 1/2. You've ignored the scale. It's up 1 square, but Emma, each square is not worth 1. And it's 2 squares over, but I'm telling you, each square is not worth 1. I generally try and find the slope between 2 points that are fairly far apart. I'm going to find the slope between here and here. How? How high is the highest point? How high? Read across. 16. How low is the lowest point? 4. What's the rise? 12. By the way, that's 1, 2, 3, 4, 5, 6 squares. It's 12. I'm telling you it's 12. Is that okay, Trish? What's the run? How far to the right is my furthest point? Drop down and read. What's it say? 7? Here? 6? There's my slope. Or in lowest terms, Dane, what is 12 over 6? I know I caught you zoning out, so I picked on you. Keep going.
And then you got to go 2 over 2. There you go.
And you'll notice if I did it just by counting, it would have been 1/2. I'm telling you, that was one thing that drove me crazy on the test. I had a whole bunch of people tell me the slope on the test was 1 over 1 because they'd set up a nice scale and gone up 1 over 1 when they graphed. Look at your scale. Okay. What's the equation? When do you guys have to go at? Okay. Well, our template is this. Slope-intercept form. Y equals mx plus b. But I really don't want to write that. I'd like to use better letters. What did I use on the y-axis of my particular graph? Sorry? That's units. What letter did I use? D for distance. The letter M in math is slope. What did we say the slope was? 2. I'm not going to write x. What letter did I use on the x-axis?
T.
What was the y-intercept?
2.
2. Sorry, too many 2's in this question, but that's just the numbers I made up. It's a fluke. D equals 2t plus 2. Big deal. Well, here's the key idea. What is the slope of this graph? What does it mean? Well, when you went, and this goes to Valoria's comment earlier, she did say, hey, Mr. Dueck, on the y-axis, the units were meters. And on the x-axis, the units are second. So this is really measuring, when I go rise over run, meters over seconds. What do I measure in meters per second? What is the slope? Velocity or speed, technically velocity. You may have memorized that last year in Science 10. Oh, the slope of a distance time graph is the velocity. You notice I just showed you how you can figure it out in 1 second by looking at the units. That's a great trick, especially if you take Physics 12. Because in Physics 12, we'll have about 40 different graphs, and no one memorizes them all. Instead, you just analyze the units, and you can figure out what it is. If it's slope, you're dividing the units. So here's the key idea. The slope of a displacement versus time graph is the velocity. It's meters over seconds. It's a velocity. What if we have a changing velocity? Example 2 says, describe what's happening over each interval of the distance versus time graph below. So I've broken it up into A, B, C, D, and E. 1, 2, 3, 4, 5 different sections. What are we graphing? Kyle, what's on the y-axis? What did I put there as a quantity? Distance. What's on the x-axis? Time. You know what the slope of this is then? Velocity. Velocity. Yep.
Why is it velocity? Because there's no direction.
Good point. You could argue it was speed as well. You could argue, though, that the direction is implied because if you were going backwards, my distance would be below the x-axis in the negative range. It's you know what? You can argue it either way. I usually use the term velocity because it's easier for kids to remember, and it goes with the V, but you're right. With no direction, you could easily argue speed. Good point. I am going to say we are going to be able to tell. You know what? I'm going to take that back. We are going to be able to tell whether we're traveling forwards or backwards based on this. So there is going to be a velocity directional component here. Watch. First of all, look at section A, the first section. What's happening to the distance? Increasing, decreasing, or stays the same as you move from the start towards the right? Increasing. Increasing. What about between section A and B? What's going on there? Staying the same. How could that be? We'll get back to that. What about between B and C? Increasing. And this is where, Michael, I think I can come back to you and I can say, what about in section C and D? What's happening to your displacement, your distance from the origin? What's happening? I think it's decreasing. Yes? I think you're traveling backwards, which does have a directional component. And D and E still decreasing, but not as fast. Not as fast. In fact, I said, describe what's happening over each interval. How will I write this here? Let's go section A, section B, C, D, E. In section A, what does that mean if the distance is increasing over time? I think it means traveling forwards. Traveling forwards. Actually, I think there's one L in traveling, which has always bugged me, but I think there is. Because it looks like it should have two, but it doesn't. B. What's happening over section AB there?
Resting.
Stopped. What about section BC? Section C.
Traveling forwards.
Can you compare that one to section A using the words faster, slower, or the same speed?
Traveling faster.
How do you know? Jeff, you're right? Okay, so forwards, comma, faster than section A. Ooh, what about section CD? Sorry? The same speed as it was going forwards? I don't know. We'll come back to that. What's happening section E? Forwards or backwards? Backwards. Slow down. Nice. Let's add that. In fact, Shaq, because we actually have numbers, I made up numbers for each point, we can actually find the average speed. The average speed. And here, Michael, I switched to speed because I started to say, well, although I can say forwards and backwards, I certainly can't say north, south, east, or west. So this is why I said it's kind of a gray area. How can I find the average speed? I think what they're saying is slope. So let's find the average speed for section A. Well, what's the rise? How high is point A? How high is point A? So that's a typo that we need to fix, Mr. Dueck. Can you make that a 20? Can you make that a 20? And I'll have to remember to fix that on my handout. Okay. So the rise is 20. What's the run? 2. Looks like section A, our average speed is 10. And I think it's meters, meters per second. What about section B? What's the average speed at section B?
0.
Yeah. What about section C? Now let me see if this makes sense. 20, 40, 60, 80. Okay, can you go up here where it says 100? Cross that out. I think that's supposed to be 120. And that's supposed to be 100. Boy, did I botch this. All right, I'm giving myself a detention. Pardon me? Roll the dice. Okay. Okay. What's the speed for section C? How high at the top? 120? How high did we start? What's the rise? 100? What's the run? I think that is 2 seconds still, yes? I got that right? 50 meters per second. That's pretty fast. Yep.
I just quickly did like a ruler measurement and D.
Yeah, D's wrong too. I'm getting there.
Okay.
I know. One error at a time, please. And at least I got E right. D, I'm good with the 8, but it looks like the height of D is supposed to be halfway between 40 and 80. Yeah, shut up. Yeah. It's been a while since I botched one that bad. But we can get the velocity now, at least. Why did I do that? It's a negative slope, right? Downhill slope we said last year was negative. What's the rise? Well, we start out at 120, we end up at 60, so it's 60 take away 120. I've already put in a negative, but I think the rise is, yes?
Yep.
What's the run?
2.
You may recall I asked, are we going backwards faster than we were going forwards? Actually, no. We were going forwards at 50 meters per second. We're going backwards at 30 meters per second, negative 30 meters per second. Last one. E. Negative. Negative 20 over 2. Negative 10, is that right? 60 to 40 is down 20 and 2 over. And again, Michael, if you argued with me and you said, hey, Dueck, that's velocity, not speed, I'd say, okay, yeah, fine. B says, what's the average velocity for the entire trip? The trick question. Velocity, we said, for a trip is displacement over time. The time is 10 seconds. What's the displacement? Where did we start at? Where did we start at? 0. Where did we end at? 40. What's our displacement? Just 40. Compare that with average speed. Oh, forgot the vector. Average speed is distance over time. Still going to be over 10 seconds. How far did we travel grand total? How far did we travel forwards grand total? 100, was it 120? How far did we travel backwards? Let's see. Looks like we went 120 forwards, and then starting at 120, we went to 40. I think 80 backwards, yes? Yeah. I think the total distance that we traveled was 120 plus 80 is 200 divided by 10. Our average speed is 20 meters per second. 20 meters per second. Okay. Turn the page. Talk about average slope versus instantaneous slope. So we're going to start to look a little, just the slightest bit at curves. Really, to analyze curves properly, you need calculus. One of the main reasons calculus was invented. But we'll just start to scratch the surface. So it says, as the slope of a displacement time graph is equal to velocity, different slopes indicate different velocities. Number 1, positive slope. Number 2, positive slope bigger than slope 1, you sped up, going forwards. Number 3, at rest. Number 4, going backwards, or, yeah, I guess going backwards. What if they give me a curve? For this, you're going to need a ruler. So if you don't have a ruler, you want to come and get one. Oh, I weep. It's going to be a little awkward for those of you watching at home because you'll be able to see what we're doing, but that's okay. Here's a distance versus time graph. We want to find the velocity right at time equals 4. So at time equals 4, I want to find the velocity. I'll put a dot right there. I go to t equals 4, and then I find where that intersects. First of all, just looking at it, can you tell me at 4 seconds, are we traveling forwards or traveling backwards? And how do you know? How do you know? Okay. The way we're going to estimate the slope is we're going to draw something called the tangent line. What's a tangent line? For those of you at home, I apologize, but those of you here, look up. Let's suppose I was talking about at t equals 2, right there. The tangent line is if I lay my ruler down and I eyeball what the slope is right there. This would be wrong. See it? This would be off, but we'll be close, kind of, sort of like that. And if you draw a line and find the slope of that line, don't do that yet. But that's how I would find a tangent line slope. We're going to do the 4. So for the 4, tell me, I'm going to put my ruler right on the point. Tell me when I should stop rotating.
Stop. No.
Keep on going a little bit more. There you go. Good, good. I think about there, isn't it? I think. Yeah. So with your ruler, draw a tangent line. I'm going to try drawing mine here. This is always awkward on the tablet. Kind of close. Then what I would do is I would find the slope of that line. I would go rise over run of that if I could. Now, I didn't give you graph paper for this particular example. I would probably argue it looks like it's slope. Looks like it goes roughly down 5 over 5-ish. But what if I wanted to find the velocity at 6 seconds? So if I wanted to find the velocity at t equals 6, I'll do that one in red. I would say right there, eyeballing it. I think kind of like that, except apparently way lower, Mr. Dueck. Okay, the thick ruler doesn't mean I can lay my ruler down where I think. I don't know. Kind of like that-ish, sort of, kind of, sort of. Now, this is a wishy-washy method in that I'll take a fair range of answers, but I wouldn't take something that was way, way off. And in calculus, you can get the exact answer. In fact, in calculus, one of the first things you learn how to do is take a derivative, and one of the first applications of the derivative is finding the equation of the tangent line, or the slope of the tangent line. Okay. Oh. I should have written here in red, t equals 6 seconds. That one there. Right? T equals 4 is the example that I gave you right here. Oh, yeah? Okay. So 4 seconds would look like the blue one. 6 seconds would roughly look like the red one. So we can use this approach to approximate the slope of a curve. So here's one with actual graph paper. We can approximate the instantaneous velocity. Now, what if we wanted to do it more accurately? You would actually need the equation of this shape, which is a weird shape, and then you can use calculus read to find any slope that you want to. And once you have the equation, it's not that hard to do the next part. It's just getting the equation would be a bit tricky. It says find the instantaneous velocity for every 30-minute interval on the graph above. So look at my x-axis. What are we measuring time in? Hours? So 30 minutes is going to be how much of an hour? So I would like you to find there, every half hour, there, and there. Let's do one together. Let's do A together. So I would lay my ruler down, and with a nice light pencil, and with my ruler right side up so it doesn't gibble. About like that. Is that close? Kind of close-ish? Then I would say to myself, hey, look, see. I go through this point, and I go through this point. 2 points nice and far apart. If I want to find the slope of line A, the instantaneous slope, the velocity at location A, I think my rise is, what's each square worth? 2.5? Is that right? So it's going to be 1, 2, 3, 4, 5, 6 squares, 2.5 apiece. What's that? How high right here? $17.5? How high right here? 2.5? So 17.5, 2.5. I think you're right, Jeff. 15. Looking at the 2 points that I used, what's my run? Well, I stopped at 2. What's each square worth here? What value is that right there? I think it's half of 0.5. Each square is 12.5. 4 squares make about how many squares? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares? Come here. 14 squares at what's each square worth? Sorry? 2.5? I think 1.25, isn't it? Because I think 4 squares makes up 0.5. So this here would be half of 0.5, 0.25. This would be half of that. Half of 25 is 12.5. Half of 0.25 is 0.125. I think that's my run. Is that okay, Trish? Let's find out. It's going to be 14 times 1.25. I get 15 over 17.5. 15, Mr. Dueck? Yeah. Over 17.5. I get 0.857. Well, how many sig figs should I go to? 17.5 had 3, but what about that 15? In fact, you could almost argue 30 minutes. Well, you know what? I'm going to go 2 sig figs. So I'm going to say 0.86 meters per second. Now, you might not have that. You might, Emma, have 0.85 or 0.84 or 0.87 or I'd probably take anything in the 0.8s. I'd probably get a little grumpy if you tried to say 0.63. I'd say you probably held your ruler wrong. Does that make sense? So take a few minutes right now, see if you can get the instantaneous slope for B, C, D, E, and F. I'm going to pause the video and freeze the screen. Okay, we're back. I went through this with my students. I also made an error on my calculator. When I calculated this, I put a 1.25 instead of a 0.125, so the first slope was 8.6. We did 4, and then we called it because we felt we were getting the hang of it. Let's answer part B. Part B, at what time or times has this person come to a stop? Okay, at what? It doesn't want dots, it wants at what time. So when t equals what? Drop down and read. Okay, at t equals 1. Any other time? There is. Ah, halfway between 2 and 2.5 for a split second there. There's a change in direction, and the only way you can change direction, unless you got magical powers, is to come to a stop for a split second. Yes? So, and you said that was t equals 2.25 seconds. That looks like 15 seconds, Mr. Dueck. Make that S look more like an S. Sorry? Oh, in hours, sorry. And I've been going meters per second in my units. Let's erase the units and let's go hours. Good gosh. Dueck, you couldn't count and you can't read. Yeah, that's what happens when I don't have lunch. Where does this person have the highest speed? Michael, speed, scalar or vector? Scalar. So I would look for the steepest slope. I don't care about positive or negative. I just try and find. Here it's not quite. I think on the way up, I think somewhere around location B. Okay. So lots of questions we can build on for this. So I have 3 short little things for us to work on. We have a take-home quiz and a couple of practice sheets for the remainder of class here. Officially, your only homework for Thanksgiving is on Tuesday. I want to mark the take-home quiz right away. The rest, if you can get it done, great, but I don't want you to have homework for the Thanksgiving long weekend. You can also finish it on Tuesday, but I'm going to be giving you more stuff.